Last time, we saw how, using Kolmogorov's extension theorem, we can construct a Markov process with any given transition kernels and any given initial distribution. We constructed that Markov process on a path space. Namely, if the time set for the process is t and the state space is s, we took as our probability space s to the t, the set of all functions from t into s. If we think of t as a continuous time parameter, then this is just the set of all paths, not necessarily continuous or regular in any way, but functions from positive time into our state space. And then we defined our process to be the coordinate process, that is, xt at an outcome omega is just the point that the path got to at time t. Defining the process this way means that we must construct a probability measure so that this coordinate process has the right finite dimensional distributions to have the given kernels. We then typically denote that probability measure as p nu, where nu is the initial distribution. So that is a probability measure on s to the t, equipped with the smallest possible sigma field that we could use in order to make all of these measurable for each t. After all, this is also just the projection, pi t, from the whole space s to the t down to s, and that's the product sigma field. The sigma field generated by those projections. It would probably make sense to index this not only by nu, but by the transition kernels q as well. We'll see going forward that it makes sense to typically think of the transition kernels as fixed from the start, but allow the initial distribution nu to vary, which is why we index the probability measure by nu. Now I want to emphasize again that we designed this construction to have the right finite dimensional distributions. And that's important because that's what we wanted, but also it's important to note that that's all we get. This construction encapsulates the finite dimensional distributions in the simplest path space construction that we can use. But not every stochastic process that is a Markov process with these transition kernels looks like that one. Now, there's the superficial fact that the process may not actually look like this, but that's superficial because we can always make the process look like that. In other words, given a stochastic process, xt, we can always identify it as a measure on path space. In some sense, we're talking about the law of the process. That is to say, given a process defined on some probability space, taking values in a state space S, we can then from it construct a probability measure, which I'm indexing as px from the process, which will be a probability measure on path space, where the measure of a set E here being a collection of paths, t mapping to, let's say, alpha of t, well, that's just going to be defined to be the probability of the set in the abstract probability space of outcomes where the path, the random path that takes t to xt of omega, is in the set E. And so this measure constructed from that process can be thought of as a version of this measure, and we can then identify this process as that one. Or can we? Here's the problem. This is a very small sigma field relative to things we might want to ask. See, this px is the law of this process, but the law is determined by what sets we're allowed to measure. And here we're allowing these to be the measurable sets that are in here. But that may be too small to capture questions we'd like to answer about the process. For example, if our time set is, say, the non-negative real line, we'd like to answer the question, are the paths of this process continuous? What's the probability that they're continuous? Well, in order to even ask that question, the set of continuous paths inside here needs to be a measurable set. And here's the problem. It's not. To say that a path alpha is continuous is to say that it is continuous at all times. And that is an uncountable constraint. That's a problem. We could cook up and ask whether the path is continuous at any particular point, but we can't ask whether the path is continuous everywhere. The set of continuous paths is just not in here when T is an uncountable set. So one solution would be to extend this sigma field to a larger one. For example, we might want to put a topology on here and then take this to be the Borel sigma field over that topological space. Now that is one way to go here, but it gets quite complicated quite quickly and will get us into some more delicate functional analytic questions, which we will need to include one way or another eventually, but that's not the approach we're going to take. One of our major goals in this course will be to construct continuous stochastic processes, but as a brief pre-introduction to that eventual goal, I just want to make sure that we all understand that properties like continuity are beyond the purview of this sigma field and beyond the purview of this construction. Let's look at an important example. Brownian motion. Brownian motion is an important continuous stochastic process whose construction is one of the main goals of this course. We call a stochastic process, relative to some filtered probability space, a Brownian motion if it's an adapted process that has independent increments, has stationary normal increments, which means exactly this. The increment bt minus bs is distributed as a normal random variable of variance t minus s for any t bigger than s, and such that the paths bt as a function of t are all continuous. Now, let's be clear here. In probability, we would usually want to say something like almost surely continuous, but as we noted on the last slide, we can't even measure the set of continuous functions relative to the kind of sigma field that we're interested in so far. So to even make sense of the statement almost surely continuous, we would need to construct a measure on the set of all paths such that these Brownian paths are with probability 1, with respect to that measure, continuous. And that measure would have to be defined on a sigma field that includes the set of continuous paths as a measurable set. Now, practically speaking, that's not how we're going to construct it. Eventually, we're going to construct it on a probability space consisting of the set of continuous paths. So we may as well say that it's continuous everywhere. Now, these conditions here didn't come out of a vacuum. They in fact appeared in the PhD thesis of a physics student. This student, in the early 20th century, was interested in the molecular theory of matter, which at the time was controversial and not accepted by most scientists. But this physicist put together a statistical mechanics model of billiard ball type particles slamming into each other and recoiling in large numbers, and found that in the large-scale aggregate, the motion of those particles bombarding each other on a small scale would look like this. That is, the aggregate behavior of the particles would have stationary independent Gaussian increments, and of course be continuous from physical constraints. So he wrote down these properties and then derived some statistics for those paths from these properties, and showed that those statistics very precisely matched observed motion of small pollen particles on apparently still ponds that was noted by a botanist, Brown, early in the 19th century. This model was therefore taken as confirmation of the molecular theory of matter and ultimately convinced the scientific community that molecules, atoms, etc. are real. For that reason, this physicist was eventually awarded the Nobel Prize for this work, and that physicist was named Albert Einstein. You might think of Einstein as the father of relativity theory, but in fact relativity theory wasn't even mentioned in his Nobel Prize nomination. He was given the Nobel Prize for the construction of Brownian motion and the explanation of the molecular theory of matter, as well as the photoelectric effect. which were 2 of his 3 important papers published in 1905, the third one being about special relativity. Now, when we say that Einstein constructed Brownian motion, that has to be constructed in quotation marks. What Einstein did was to show from a statistical mechanics model that the aggregate behavior of particles in the large scale would look like this, and then decided, therefore, such a process must exist, and we can derive properties from it. This was before the language of stochastic processes even existed. It took another 20 years after Einstein published this paper before mathematicians were able to successfully construct a stochastic process with these properties. And I'll talk a little bit more about that on the next slide. But first, let's note, using what we know so far, we can construct a stochastic process with the first 2 properties here, because these describe the finite dimensional distributions of our process. So what we can do is construct a Markov process which satisfy 1 and 2. That is, in order to get those independent increments, as we know from your homework, what we have to do is define our transition kernels, QST, of a starting point x and a Borel set B, to be the expected value of the indicator of B of x plus the increment, bt minus bs. Now, this is turning things around a little bit. You showed on your homework that if you have an independent increment process, then it is a Markov process with this as its kernel. Now we're saying let's define the kernel to be this. Does that mean that we can construct a Markov process with these kernels? Well, we know from Kolmogorov that we can, provided that these kernels satisfy the Chapman-Kolmogorov equations. So let's just check that. First of all, let's write out what this expectation is. From property 2, together with 1, which we've now incorporated, that means that this is the integral over the Borel set B of the Gaussian density of variance t minus s and mean x. That's what this random variable is. So we can write out that density. Like so. So to construct a Markov process satisfying properties 1 and 2, it suffices to show that these are Markov transition kernels, that they satisfy the Chapman-Kolmogorov equations. The first one is we need to check what happens to QTT. Well, since BT minus BT is 0, that means that QTT of x and b is the expected value of the indicator of b at x, which is exactly equal to 1 if x is in b and 0 if it's not. So that is delta x of b, and that's the first Chapman-Kolmogorov equation, that QTT is the point mass at x. Now for s less than t, let's work in terms of the transition operators. QST of a bounded measurable function is the integral of that function against the transition kernel, so that's this right here. And now we can just recognize that that is an integral of this function against the Gaussian density of variance t minus s evaluated at x minus y, which is exactly our definition of convolution. This is the convolution of, I'm going to write the Gaussian density, gamma t minus s, convolved with the function f at x. Now, we focused on convolution of probability measures and therefore probability densities, but convolution of functions makes perfect sense in general, whether this is a probability density or not, as long as this integral makes sense. And since this is a nice L1 function and this is a bounded measurable function, there's no problem defining that integral, or showing that convolution has the usual properties that it does. And so we can therefore check the composition. QRS QST applied to a function f, just doing that in turns, is QRS of gamma t minus s convolved with f. Now here's our new function. You can check that this is going to be a bounded measurable function, since it's the convolution of two bounded measurable functions, and therefore it's in the domain of this transition operator. And we again get from what we've written above, this is gamma of s minus r convolved with that, gamma of t minus s convolved with f. Now we know that convolution is an associative operation, so we can move the brackets over. This is gamma s minus r convolved with gamma t minus s convolved with f. Now here's the thing. What does that convolution mean? This is a convolution of two probability densities. This is the density of a random variable y, which has distribution normal, centered, variance s minus r. And this one is the density of a random variable z that is normal, centered, with variance t minus s. And so that convolution there is exactly the density of y plus z if these two are independent from each other. Well, we know that if I have two independent normal random variables and add them up, then we get a normal random variable, still centered of course, and its variance is the sum of the variances of the two. So that's s minus r plus t minus s, which is t minus r. And so that gives us gamma rt convolved with f, which is exactly the transition kernel qrt of f. And there we have it. The Chapman-Kolmogorov equations are verified. So using Kolmogorov's extension theorem, we know we can construct a stochastic process, a Markov process, in fact, that has the right increments, independent, where the distribution of each increment is a Gaussian, whose variance is the length of the time interval. Now what about property 3, incorporating continuity of the paths? Well, as we noted, it doesn't even make sense to ask that question, given the construction that we already gave. The stochastic process defined on the path space equipped with the minimal sigma field doesn't include continuous functions as a measurable set. So we can't ask what's the probability that these paths are continuous. This construction won't cut it. We're going to have to develop a lot more tools in order to construct a continuous version of this path. Now, one approach would be to do an explicit construction like we did for the Poisson process. That is, maybe we can just construct a stochastic process not using some abstract tool like Kolmogorov. And in fact, that is possible. And here is one standard way to do it. If you take an infinite IID sequence of standard normal random variables and take this series in them, that is Cn over n times this trigonometric function appropriately renormalized, that sum will be a stochastic process, Bt, which has all three properties that Einstein posited. It will be a Markov process with these transition kernels here, and its paths will be continuous. That was the approach that Norbert Wiener took in the mid-1920s, 100 years ago, in order to give this explicit construction. You already showed on an early homework set this quarter that this series actually converges almost surely for each fixed t. What Wiener did was to show that this series converges uniformly in t for t in any compact set. And since the finite partial sums here are all trigonometric polynomials, therefore continuous, it follows from uniform convergence that the limit will also be continuous as a function of t. Now that approach is quite challenging, and Wiener's original paper is perhaps worth reading to see what methods were used. Even coming up with this representation takes some work. This is, of course, the Fourier series of a Brownian path. The tools that Wiener developed in order to prove this uniform convergence and continuity formed the foundation upon which later luminaries, Kolmogorov and Lévy, used to formulate what we're now presenting as the theory of stochastic processes. So we're not going to go through this explicit construction. We will use some tools and tricks that Kolmogorov and others developed later in order to show that the stochastic process we built earlier has a continuous version. But I want to hammer this point home even further. Explicit constructions inherently give us more information than the finite dimensional distributions, which is all the transition kernels can tell us about. So I'd like to spend the rest of this lecture examining again the Poisson process that we constructed earlier. Remember that we constructed the Poisson process as the counting process of a renewal process. That is, we started with an IID family of exponential random variables and considered their partial sums. That gave us our renewal process. And then for each positive real time t, nt was defined to be the largest index n for which the partial sum xn was less than or equal to t. We showed explicitly that that process has these properties. It had independent increments. The increments were distributed as Poisson random variables, with the mean being a multiple of t minus s, that multiple being lambda, the rate that we built in over here. And importantly, those paths were not continuous, of course, since they're piecewise constant, but right continuous and non-decreasing. That is to say, the paths typically look like this. You have jumps of height 1, and at the jump, the value of nt is always at the top, not the bottom or somewhere in between. Now, we arrived at these properties naturally from this construction, but we could turn the tables here and say, let's construct a Markov process which has these properties. And we're in the same pickle here with property 3, because the set of right continuous paths is not a measurable set in the product sigma field. So we would need to have a larger sigma field in order to even ask the question whether these paths are right continuous or increasing. Same problem. However, we can do the same thing that we just did with Brownian motion, or what we might call pre-Brownian motion, before we are able to make it continuous, and construct, using Kolmogorov, a Markov process that has these first two properties. The way we would do that is exactly the same. We write down the kernel that we know we have to have if we're going to have these independent increments, and that is using this formula right here. Now, in this case, where the state space is discrete, the natural numbers, the kernels are better described in terms of a probability mass function. That is, QST of a point n and a set B of natural numbers is just going to be the sum over all the natural numbers m in that set of QST of n and m. So we have a kernel mass function. And therefore, to construct this process using the Kolmogorov extension theorem, we need to check that these kernel mass functions satisfy the appropriate version of the Chapman-Kolmogorov equations. Of course, this being this expectation here, being the indicator of just the set M singleton, means we're looking at the probability that n plus this increment is equal to m, and subtracting n from both sides, and using property 2 here. What that means is that the value of this is just the Poisson probability mass function with this rate at m minus n, which we can write down as a simple exponential polynomial function. Now, I'm not going to go through the calculation from here, but I'll just note that we have already done several times the calculation that if I have two independent Poisson random variables of different rates, then their sum is a Poisson random variable whose rate is the sum of the rates. And so you can use that here to follow a derivation, much like the one we did for Pre-Brownian motion, to verify that these kernels satisfy the Chapman-Kolmogorov equations, and therefore we can construct abstractly on path space a Markov process that satisfies properties 1 and 2. Now, before we get to this more complicated question here, what else can we say about that abstract Markov process? Well, it turns out that we can more or less get back to where we started, and that is the following theorem. If we construct any process nt, which satisfies those properties 1 and 2, that is, it has independent increments which are appropriately Poisson distributed, then we can recover those exponential interarrival times. If xn is the smallest time t where nt takes the value n, and if cn is the interarrival time between xn and xn minus 1, then those cn's are actually IID, exponential random variables. So to prove that, we're going to look at these xn's. Where do those xn's live? Well, it's important to note that at least for fixed s and t, nt minus ns is Poisson, and Poisson distributions are supported on the non-negative integers, so in particular this means that that's greater than or equal to 0. So from that we see that xn plus 1 must be greater than or equal to xn with probability 1. Therefore, if I look at the whole sequence, x1, x2, up to xn for some fixed n, the values they take have to be increasing. So if I want to look at a set in R to the n where the vector x1, x2 up to xn lives, it actually has to be in the set little x1 up to little xn where x1 is less than x2 up to is less than xn, as we did with our construction. Now let's actually be even more precise and persnickety than that. Let's specify a collection of intervals. We're interested in the probability that x1 through xn lie in a certain n tuple of intervals, j1 through jn. If that's going to happen, then those j1 through jn should be, in some sense, an increasing family of intervals. So let's make them actually increasing, which is a stronger constraint. That is, let's fix a partition of intervals. S1 up to T1 is going to be J1. S2 up to T2 is going to be J2. Up to Sn up to Tn is Jn. So in this picture here, J1 is here, J2 is here, and so on. So we're going to take those intervals so that each interval is above the previous one fully. Now it'll also be useful in our calculations to look at the interleaving intervals. That is, the interval right here between the top endpoint of J1 and the bottom endpoint of J2. Let's call those intervals K. So actually K1 is going to be down here from 0 up to S1. K2 is here. In this example, K3 is empty. Here's K4, K5. So we're going to compute the probability that the x1 through xn defined from our abstractly constructed Poisson process as the corresponding arrival process, that random vector lies in the product of these intervals. Well, that's just a matter of writing down exactly what this event means. What does it mean that x1 is in J1, x2 is in J2, up to xn is in Jn? To write that down succinctly, we'll introduce some notation, which is consistent with our stochastic measure notation from before. If we have this process nt, let's set n of the half-open interval from s up to t to be just the increment, nt minus ns. So with that notation in hand, what does it mean to say that x1 is in J1 and x2 is in J2? That means that the process jumped to height 1 somewhere in between S1 and T1, which means that from 0 up to S1, it was 0. So that says that the increment n of S1 minus n of 0 is 0. That is, this is 0. And it also means that the increment of the process between S1 and T1 here is 1, because I got a jump from 0 up to 1 in that interval. Now, if I look at the next datum I have here, x2 is in J2. Well, that says that, again, there was no jump in the interval between T1 and S2. So n of K2 will be 0, and n of J2 will be 1. And we can continue this all the way down this line and get that this is described by all of these conditions here, except there's a kink when we get to the end. All we know is that xn is in Jn. But it could be that xn plus 1 and xn plus 2 and xn plus 3 are also in Jn. All we know is that the increment from Sn up to Tn has at least one jump in it. So that's what we can say there. This event is equivalently described by the intersection of these events here. And the key is that all 2n of these events are independent from each other, because they're all described in terms of disjoint increments. That's the way we've designed it. Well, that's great, because that means we can just write down explicitly what the probability of this event is in terms of the increments. Property 2 that we declared for this process is that the increment n of j is a Poisson distributed random variable with rate lambda times the Euclidean length of the interval j. And so that means that the probability that n of j is equal to any positive integer n is e to the minus lambda length of j times length of j times lambda to the n divided by n factorial. Now we can sum those up as well and note that therefore the probability that the increment n of j is greater than or equal to 1, well, that's 1 minus the probability that it's 0. But plugging in n is equal to 0 in this formula tells us that this is just 1 minus e to the minus lambda j. And so using the independence of the increments over here, we therefore have that this probability here is a product. It's a product first over the k's, so that gives us the product of e to the minus lambda length of kj. And then a product over the j's here, those are all equal to 1, so using this formula with n equal to 1, those are all e to the minus lambda length of j times lambda length of j. And then finally, we have one more term, which is this one here, and that's what we just calculated there. So that's 1 minus e to the minus lambda jn. So there we have a completely explicit formula, and we can nicely simplify it. Let's take these lambdas, there are n minus 1 of them, out of the product. So that's lambda to the n minus 1. Let's combine these two products with each other. Problem is that there's an extra one hanging out over here, so let's take the product up to n minus 1 in both of them, and take that extra term out at the end. So this is the product j going from 1 up to n minus 1 of length of j, e to the minus lambda length of j, e to the minus lambda length of k. And then at the end, we're left over with the j equals n term in the first product. So that's e to the minus lambda length of kn times 1 minus e to the minus lambda length of jn. Okay, now we can simplify this nicely because here the interval j is given by tj minus sj, and the interval k is given by sj minus tj minus 1. And because we're adding up exponentials here with the same rate, that's summing those. And the thing is that those sj's are going to cancel, so we just get an increment of the t's from there. And then we're going to take a product of those, which will turn into an exponential of the sum of those increments, but that's a telescoping series. So all of that is just going to reduce to e to the minus lambda times tn minus 1 minus t0, and t0 is just 0. That's all of these terms here, incorporated here in the product. What we're left over with is still this product here. And then these terms here. We can write out what these are in terms of the endpoints of those intervals, and what we get is this. And now we're going to get some more nice cancellations between here and here and here and here. Well, there's still that one minus. So if we do all of that carefully, what we find is that all of the exponential terms here combine into a single difference, and it's this difference here, e to the minus lambda Sn minus e to the minus lambda Tn, and we're just left over with these product terms there. And now, I'd like to note that this difference here is exactly the integral over the last interval Jn of lambda e to the minus lambda xn dxn. I'm suggestively using the integration variable xn because we recognize this as the density of an exponential random variable in the last variable. And of course, this product here is the volume of an n-1 dimensional rectangular prism with side lengths given by those intervals. And so putting this all together and incorporating this lambda with that one, we get lambda to the n, the integral over the product of all of those intervals, e to the minus lambda xn dx1 through dxn. And there's our very simple formula for the probability that the arrival process x1 through xn vector lies in this product of intervals. That should, of course, look familiar to you. You showed on a homework set that if you start with IID exponential lambda interarrival time random variables and define the x's to be their partial sums, then the probability that that vector lies in any particular Borel set in this configuration space is given exactly by this formula. And in fact, that's what we've shown here as well, because as I'll leave you to verify, with Dinkin's help once again, the sigma field generated by the set of all products of those stacked intervals is exactly the Borel sigma field over the configuration space, delta n. And so that shows, by Dinkin, that this formula holds for all such b's. And now you can reverse engineer that change of variables calculation that you did to show that this shows that the differences, ck, between subsequent xn's are, in fact, IID exponential random variables, as we claimed. So we can actually get pretty far from this Kolmogorov construction of this Markov process. We do get IID exponential interarrival times. However, that third property about the right continuity of the paths of the process is just beyond our reach. We can't get that from here. And one quick way to see that is to do a construction just like we did originally for the Poisson process. Let's take an IID sequence of exponential lambda random variables and define a process MT like this, just like we did before, except there's one crucial difference. Before, we took the interval open 0 up to closed t. Now, we're going to take this interval, where Cn is positive but strictly less than t. Then you can go through the calculations we did originally for the Poisson process to see that this thing has exactly the same finite dimensional distributions as our standard nt. But with this constraint here, what we have is that the event that mt is equal to n is going to be the event that xn is strictly less than t, and t is less than or equal to xn plus 1. Whereas before, we had less than or equal to here and less than there. What that means is that the paths of this process, mt, look like this. They are not right continuous, they're left continuous with jumps of height 1. So the moral of that long story there is that you can go a long way from the finite dimensional distributions. The transition kernels give you a lot of information about the process, but they cannot give you really delicate path properties like continuity or right continuity. Those path properties are outside the purview of the Markov transition kernels.